Hello, everyone, and welcome again to your channel of probability and statistics. Last time we were looking at some discrete probability distributions like the binomial, the geometric. And I think in the geometric, I never mentioned the variance. Just as a quick thing, remember the geometric was telling you it gives you the probability that you get the first success on the nth trial. Okay, so if I want to know, I'm going to flip a coin. What is the likelihood that I won't get ahead until the fourth flip? Then you would say, okay, so I have to have a tail, a tail, a tail, then a head. And we said that for the geometric distribution, the mean, we mentioned it was 1 over p, which makes sense. If it's 50%, then you expect it every 2 times. If it's 10%, you expect to get one every 10 times, and so on and so forth. The reciprocal. The variance, on the other hand, in fact, we did that, even we proved it mathematically, but it's a lot of work. It's not worth it. Here you get 1 minus p over p square. And again, the way to do it is too complicated. It's not, again, worth wasting your time. Okay, so if we move after that and look at the next distribution I want to go, maybe I will go over two. There are many, like we are going to do the negative binomial and the Poisson. These are pretty much the most important along with the previous two. Especially the Poisson, because the Poisson and the binomial, you can use them in quality control and in other classes. The negative binomial, I'm going to discuss it now. There is the hypergeometric. And probably that works for, like, if your population is not infinite, it's finite, like you have playing cards and you want to find the probability of getting, let's say, a full house just once you are dealt before switching cards. So what is this likelihood? So the hypergeometric would give you that probability, and there is the mean and the variance of those established. There is the multinomial. Notice multinomial meaning we did the binomial, meaning we had only two possible outcomes. What if they were five possible outcomes? Okay, and you know the probability of success for each, and now you want to find, how many of each you will get if you run the experiment n times. Again, these are very rare to encounter unless you are a mathematician and you are going to work in this area. Okay, so what is the negative binomial then? Negative binomial. And why it was called negative? Well, I think a better name would have been inverse binomial because there is nothing negative about it. Just to refresh your memory, when we did the binomial distribution, we said we will run an experiment n times. So n was fixed. And I could find the probability of getting x successes in these n, right? X successes and n minus x failures. But I fixed the number and I was looking at the successes, the number of successes. So the total number of experiment was fixed and the number of successes was the random variable. In the negative binomial, it's the other way around. You are going to say, what is the probability of getting the fourth success in the seventh trial, for example? Okay, so you don't, so you fix the number of successes in a given interval, so to speak. So it's not really negative binomial, but it's the opposite, so to speak. So let's define, for example, R is the number of successes. Again, there is no like agreed upon letters to use the negative by some use X, some use N, some use R. It's all over the place. So the important thing is that you understand these parameters and what each one we will use means. Like before, to reduce confusion, we are going to say P is the probability of success, and 1 minus P or Q is the probability of failure. Okay. And then maybe we can call, uh, maybe we should, I don't know. You can use X as the number of failures. And I think the way it's easily explained is the following. Suppose, as I said, I want to find the third success in the any number, eighth trial. That means, notice I didn't say three successes and five failures. No, the third success is the eighth trial. So definitely I would have five failures, right? But I don't care about when was the first success, when was the second success, and so on and so forth. So let's see the way we do it. We say, let's see, I know for sure after seven trials, I will have two successes and five failures. What is that probability? It's seven, take two, right? If I do it successes, if I do failures, say seven, take five. It doesn't matter. It doesn't matter. We didn't do, oh, here we have this 7, 2 is this number, 7, 5 is that number. It's 21 and 21. It doesn't matter, right? So we don't care whether we count from the right or the left, but 7 take 2 or 7 take 5, both of them are correct. Notice I'm using the binomial now. I said, what is the probability that I get two successes and five failures in seven trials? So that's a binomial, right? Okay. So 7 take 2, p to the second power, because I have two successes. 1 minus p to the fifth power. But now the next has to be success, because here in the first seven, I had two successes and five failures. I want the third success to be the eighth trial, so I multiply by p. So basically it becomes 7 take 2, p cubed times 1 minus p to the fifth. It's so easy. That's the probability of our successes. But if you want to write p here, the probability of getting, for example, R successes in R plus X trials and N, when N is the 8 here, it doesn't matter, you don't even need to write N. We are going to write this thing. 7 take 2. So what is 7? 7 is the total number of trials minus 1. But what is the total number of trials minus 1? It's successes plus failures minus 1, right? And I want here to have X, or you can write this as, you can write it as X, the number of failures, or you can write it as R minus 1. Both are correct. So either this or that. Both of them are the same. We saw that 7 take 2 is the same as 7 take 5 in this example, times P to the R, P cubed, P to the R, it's the same, 1 minus P to the X, which is the number of failures. Here, the mean, wow, the mean is similar to the geometric, but it's R over P. No, instead of saying 1 over P, it's R over P. And the variance, again, the same thing. Instead of being 1 minus P over P squared, it's R times 1 minus P over P squared. Okay, and here you can think of this as the example that we can go over. I want to find the third success. And if I give you the probability of success, then you can do it. You just substitute that for P. Okay, so that's the negative binomial, very similar to the binomial, but instead of fixing the number of trials and looking for the number of successes. I'm fixing the number of successes, and then I can say, what is the probability that I get the third success in the third trial, or the third success in the fourth trial, or the third success in the 10th trial? So now the number of trials is not fixed. I can change it as I want, but the number of successes I have fixed. So that's why they call it the negative binomial, meaning, or the opposite of the binomial or something like that. Okay. As I said, I want to show you also the Poisson distribution, because Poisson distribution is very important. You will use it in many other classes, like the binomial also. And the Poisson distribution is another discrete distribution. But then here the parameter given to you, I think most people use mu and some use lambda, but they don't want to use lambda so that it doesn't get confused with the exponential. Don't worry about that. But it's so if we say p of x, the probability of having x successes, or x, you found x elements in that distribution, that I would explain it. It's e to the negative mu times mu to the x over x factorial, and x here equals 0, 1, 2, till infinity. So what is E? You know, E is 2.71. It's the base of the logarithm, the natural logarithm. Mu here is a rate. I will give you an example. Suppose I tell you during normal hours, not rush hours, the cars coming to the drive-through of a particular restaurant are 5 per hour. Okay, so mu here becomes 5. Okay, so it's a rate, or number of defects, say in a in a piece of cloth, number of defects per square feet. Or you hire someone as a typist, and on average she's doing 3 mistakes or 3 typos in a page. So always it's a rate, okay? And then I ask you, okay, so the 3 typos in a page, what is the likelihood that if I give her, say, some document to type and it's 10 pages, what is the likelihood that she will get less than 25 errors or more than 40? So errors per document, or error per page, or cars per hour or per minute, or whatever. It's always per, it's always a rate. So let's take an example. Suppose we said we get 5 arrivals per hour. Okay. The arrivals can be anything: people coming into a store, cars going into something, machines that fail. But 5 per hour would be humongous, but 5 per month. You get 5 machines from different areas that you repair per month, or something like that. Okay, a rate again. That's on average. What is the likelihood you get 5 buses per hour? Same thing. Okay, what is the probability, or the likelihood, or the probability of getting exactly 3, or less than 4, or more than 2, whatever? These are the probabilities. Okay, so we can say, for example, if mu is 3 and we want to find the probability, I'm sorry, if mu is 5 and we want the probability that you get 3, you say P of 3 equals e to the negative mu, which is 5, times 5 cubed over 3 factorial. E to the negative 5 times 125 over 6. And then you can evaluate that. E to the negative 5 times 125 over 6. And you get the probability is 0.14. What is the probability of getting um, less than 4? Less than 4 meaning we already got the probability of 3. So probability of 0 plus probability of 1 plus probability of 2 plus probability of 3, which is 0.14. So you say e to the negative 5 doesn't change, e to the negative 5 times 5 to the 0 is 1 over 6. So over 6, you get 0.0011. And then you go back and you say times 5, right? You get that because 5 to the first is 5 instead of 0. So you multiply by 5 and you get 0.0056. And then you say, okay, so uh, oops. Yeah, over because here, okay, this guy was e to the negative 5 times 5 to the 0 over 0 factorial, and 0 factorial is 1. This one is e to the negative 5, 5 to the first over 1 factorial, but 1 factorial is also 1, so that's why I just multiplied it by 5. When we go here, you say e to the negative 5 times 5 squared, which is 25, over 2, because 2 factorial is 2, and you get 0.084. Okay? And then you add those up, so you get this guy plus, oh, we didn't get the first one, this guy plus this guy plus that guy. And you get this number is 0.2313. Finally, what if I say, what is the probability of getting more than 2? More than 2, meaning 3 or 4 or 5 up to infinity. Nobody can add those. Oh, but we said that the sum of all the probabilities from 0 to infinity is 1. So a clever way is to say 1 minus the probability of 0 plus the probability of 1 plus the probability of 2, because I don't want 2, I want more than 2. So I subtract 0, 1, and 2. And I say that's easy. I'm going to say 1 minus the probability of 1 is that, minus the probability of 2 is that, minus the probability of 0, probability of 1, and the probability of 2 is that. That's it. And I get 90.9%. 0.909 is the probability that I will get more than 2. Yeah, of course, if the mean is 5, you expect, to have not 0, 1, or 2. These are, very small numbers. But we could have subtracted the 0.14 from that, by the way, because, or no, we have to subtract 2 and 3. Okay, so it doesn't matter. What we are saying is we said less than 4, right? Yeah, so we want less than 2, which, yeah, you have to subtract these 2 and then subtract them from 1. No, that's much easier. We say that the mean here is the same as the variance, by the way. Both of them are the same, and they are equal to mu. So the mean is 5. The variance is 5, meaning the standard deviation, sigma, is root of mu, roughly 2.2 something. Okay. It turns out that if mu is an integer number, let's find the probability of 5 and the probability of 4. This guy is e to the negative 5, 5 to the fifth, right? Over 5 factorial, and this is e to the negative 5 times 5 to the 4 over 4 factorial. These two numbers would be the same. Say what? Yeah. The numerator, the top one, I can write the numerator as e to the negative 5, 5 to the 4 times 5, right? And the denominator 5 factorial is 5 times 4 factorial. Now these two cancel, and you get the same result. It's just a property that I thought it's worth mentioning. Um, that for the Poisson distribution, if the mean, which is the rate, is an integer, then p of the mean and p of the mean minus 1 would be the same. P of mu and p of mu minus 1. I think that's enough for discrete distributions. In the next session, we will start continuous distribution because that's the more likely we'll be using it in the rest of the course. Okay, I hope this was an easy and light session, and I hope to see you soon.